Welcome to all. So, we will be starting with the elastic and plastic deformation. So, we will be talking about the different types of mechanism of defect generation in the elastic and plastic deformation. We will be looking into the high strain rate and we will be looking into the propagation of the plastic deformation under shock waves. Okay. So, here we will be looking into the physics of plastic deformations. Okay. So, under high strain rates, okay, under high strain rates meaning under shock loading, blast loading or under severe high strain loading, how the plastic deformation takes place. Okay. We will be talking about mechanism of defect generation, okay, and this thing will be done under the rate sensitivity assumptions. Okay. Rate sensitivity, as we have seen, as we increase the rate of the loading, the behavior of the material changes. Okay. It will become tougher, the Young's modulus will slightly increase, the tensile stresses and the ultimate stresses are increasing. Okay. So, this is the increasing phase of loading. Okay. The rate of loading is increasing. Okay. So, if this is E1 epsilon 1 dot, epsilon 2 dot, epsilon 3 dot, it means that epsilon 3 dot is greater than epsilon 2 dot and epsilon 1 dot and subsequently. Okay. So, this is the way how the strain rate increases. Okay. So, we will be looking into the point defects that propagates. Okay. We will be looking into the line defects, we will be looking into the interfacial defects that occurs normally during the composites, and we will be looking into the phase transformations. Okay. Moving ahead. So, we will be looking into the strain rate sensitivity. So, what is strain rate sensitivity? So, strain rate sensitivity, as we have seen earlier, it refers to how a material's mechanical properties, okay, like strength and toughness changes with the increase of loading or with the change of speed of deformation, okay, especially under impact or blast conditions. Okay. How does it matter? Okay. Why this thing matters? Okay. This thing matters under the energy absorption. Okay. So, high strain rate effects, okay, that take place during impact event, crash events and explosions. Okay. So, during rapid loading scenarios, okay, where the magnitude of the force is very high and is applied over a very less amount of time. Okay. So, if this is applied in the millisecond, okay, as in the case of impact or in the case of blast. Okay. This is the pressure and this is the time again in millisecond. Okay. So, during this event, okay, what will happen is that the physical properties, okay, strength, modulus of elasticity, toughness, okay, they subsequently changes, okay, and the total area under the energy absorption curve also changes. Okay. So, these are very crucial for analyzing the energy absorption capacity of the different materials. Okay. So, there are materials with positive strain rate sensitivity. Okay. It becomes stronger as loading rate increases. Okay. It absorbs more energy before failure and it shows better performance in the dynamic event. Okay. So, if you look into the typical stress strain curve at different strain rates. Okay. So, here we are considering the what is called known as the static strain rate, means the rate of loading is very small. Okay. So, we can consider this as a static event. Okay. So, in the static event, this is the typical stress strain curve. Okay. So, this value is typically known as the yield stress. Okay. So, as we increase the rate of the loading, okay, so here the rate of the loading or the strain rate is in the less than 10 per second, okay, 10 units per second. Okay. And as we increase the rate of the loading, okay, we are moving into 1 to 1000 per second strain. Okay. And here we are looking into very high strain rates, okay, more than 1000 per second. Okay. So, here we can see the value of sigma y is increasing. So, we can call this one as a static stress and here we can call this one as the dynamic stresses. Okay. And with the increase in the strain rate, this value is increasing. Okay. And we can also see that there is a slight increase in the modulus of Young's modulus also. Okay. So, the material is becoming tougher and tougher. Okay. If you look into the total area under this curve, okay, we can see that the total area if we compare with the static strain, okay, if we can call this one as the area 1 static, area 2 dynamic 1 and area 3 dynamic 2. Okay. So, with the increase in the strain rate, the area under the stress strain curve also increases. It means that the energy absorption capacity also increases. Okay. So, the material is becoming stronger as well as the energy absorption capacity is becoming more and more. Okay. So, higher strain rate, higher peak stresses. So, peak stresses are higher, here we can see the increase in the peak stresses and it has a steeper slope. The Young's modulus also increases. Okay. So, the material is becoming more stiff. Okay. At higher strain rate, the area under the curve increases. So, the energy absorption is also more out here. Okay. So, this establishes the fact that during the high strain rate, the material is behaving in a positive sense, that it is increasing its capacity to absorb energy and it is becoming stronger and stronger. Okay. So, key aspects of the strain rate sensitivity in ductile materials. Okay. So, what happens in the strain rate sensitivity when we are dealing with the ductile material? Okay. So, we are calling strain rate sensitivity as SRS. So, if SRS is positive, so it contributes towards the ductility and deformation stability of metals and alloys. So, for a ductile material, if SRS is positive, okay, it will play a key role, a pivotal role in controlling the ductility and deformation stability of the metals and alloys. Okay. So, higher SRS values tends to delay strain localization phenomena. Okay. So, the failure mechanism, okay, will be delayed due to the higher strain rate sensitivity value, okay, such as necking, okay, and it will ensure that a uniform elongation during the tensile test results. Okay. So, what does it mean? Okay. So, if the material is under static loading, okay, so what is going to happen is that as we increase the loading, okay, sigma y is reached early, okay, and the necking process will start. Okay. If the rate of loading is increased, okay, so if this is strain rate static and this is strain rate dynamic, okay, then the value of sigma y is significantly higher, okay, YD1, then this necking process will be delayed. Okay. So, this is the meaning of the delay of the strain localization phenomena. Okay. So, SRS value, it also acts against strain localization by increasing flow stress locally, where strain rate intensifies, promoting more distributed deformation. Okay. It means that this localization of the strain, okay, at a particular point, okay, is also delayed. Okay. So, the thing will be more uniformly deforming. Okay. So, the distribution of the load, okay, it will be more uniform. Okay. In the static one, the necking will start to form earlier, okay, but in case of the dynamic loading, the necking will be delayed and the stress distribution in the cross section will be uniform. Here we can see the stress distribution is non-uniform. Okay. The amount of stress here will be larger than this area. Okay. So, what is the typical behavior? Okay. So, ductile metallic alloy usually exhibit low SRS at room temperature. So, at room temperature, okay, the ductile material have low strain rate sensitivity. Okay. And as we increase the temperature, okay, we are denoting the temperature in terms of Tm. Okay. The melting temperature, the value of the strain rate sensitivity increases substantially. Okay. It means that at the higher temperature, as the temperature approaches the melting temperature, the strain rate sensitivity will also increase. Okay. So, superplasticity, okay, characterized by very high elongation. Okay. When the material is undergoing very high elongation, okay, so it will occur with the elevated temperature. Okay. So, during the elevated temperature where the strain rate sensitivity is more, the occurrence of the superplasticity will take place. Okay. And the mechanisms such as grain boundary sliding and diffusion creep will also takes place. Okay. So, basically intermolecular interaction will occur in the metallic alloys. Okay. So, there will be influence of the microstructural configuration also. So, grain size will strongly affects the strain rate sensitivity. Okay. So, ultra fine grains and nanocrystalline materials show enhanced strain rate sensitivity due to grain boundary mechanism. Okay. So, due to the inherent intermolecular interactions, okay, if the grains are very fine, okay, such as in the case of nanocrystalline materials or ultra fine grain metallic materials, the strain rate sensitivity is more. Okay. What actually happens is that this smaller gains extend the range of deformation condition supporting high SRS. Okay. So, since the grain size is smaller, the interaction is more, okay, and hence the strain rate sensitivity is increased. Okay. So, for very fine grain materials, the strain rate sensitivity will be more. Okay. So, if we want to model this thing, okay, the grain boundary sliding in a mechanical way, so we have to develop different mechanical models. Okay. So, some commonly known models are models such as the grain boundary sliding model. Okay. So, if we have a developed grain boundary sliding model, okay, so it will predict the nonlinear relationship between the flow stress and the strain rate, where SRS will vary within the material properties. So, it will vary with the material properties, grain size, temperature and strain rate. Okay. So, our strain rate sensitivity will vary as a function of grain size. Okay. Smaller the material, higher the sensitivity. It will vary with temperature, higher the temperature, more will be the strain rate sensitivity, and obviously the strain rate, higher the strain rate sensitivity will be more. Okay. So, these are the strengthening mechanisms. Okay. This increases the inherent properties of the materials. Okay. So, other strengthening mechanisms, okay, they are normally related with the thermal aspects. Okay. So, they will exhibit at higher temperature conditions, okay, and they affect the threshold stresses, okay, and they normally combine with the grain size. Okay. So, what is happening if we have a very smaller grain size, okay, the interaction among the grains will be more, okay, and due to this increased interaction, okay, the movement of this intermolecular particles will be more, and then they will be affecting the strength requirements, they will be affecting the total plastic conditions, okay, and they will increase the mechanical properties of the material. Okay. So, other aspect, that is the temperature. So, the temperature affect the strain rate sensitivity both by altering diffusion coefficients and changing flow stresses due to the thermal activation. Okay. So, during the higher temperatures, the strain rate effects are also enhanced more, okay, due to the diffusion occurring and due to the flow stresses occurring. Okay. So, material behavior at various strain rates. Okay. So, at low strain rates, okay, defects can accumulate leading to strain hardening and heterogeneous deformation. Okay. So, at very high strain rate, okay, different physical mechanisms such as adiabatic heating, dynamic strain aging, deformation twining will influence the strength and ductility, okay, and they will severely affect the strain rate sensitivity. Okay. So, practical importance and applications of the SRS, okay, practical importance of the SRS phenomena. So, we need to understand the strain rate sensitivity phenomena, okay, because we need to characterize the strength of the material as well as the energy absorption capacity. Okay. So, this understanding of this phenomenon is essential for optimizing the formability, especially in the, if you are working in the metal forming area. Okay. So, the amount of formability, okay. So, how much this thing can be molded into, okay, will depend upon the strain rate sensitivity. Okay. So, this understanding is required. Okay. And when we are manufacturing material, so we need to understand the grain size and the controlling temperature, okay, and the effect of the strain rate sensitivity on these factors. Okay. So, that way if we can control the grain size, if you can control the temperature, if you can control the strain rate, okay, we can actually design a material, okay, which has a better performance, okay, under the energy absorption phenomena. Okay. And desired ductility, it means that the increased stress strain behavior, okay, this behavior can be molded, okay, depending upon the controlling of the inherent material properties. Okay. So, for high strain rate behavior, so in application involving impacts, crash, ballistic events, explosions, SRS, the strain rate sensitivity affects the strength and the toughness. Okay. This we have seen. Okay. So, we need to have a very good understanding of the constitutive models, okay, of the strain rate behavior, meaning this behavior, okay, we should be able to formulate this behavior in terms of equations, okay, where this behavior is represented in form of basic quantities. Okay. So, the stress is represented in terms of basic quantities like strain rate, modulus of the material, and so on and so forth. Okay. So, using this constitutive model, okay, one of the widely used model is Johnson-Cook model. So, using this constitutive model, we can use this material model in our simulation, in our finite element simulation, or in our analytical calculations for predicting the material response, the behavior of the material, the behavior of the structure by which this material is made, and the effect it will have, okay, as an energy absorption material or as a sacrificial cladding, okay, to act against the dynamic events, okay, like a crash event, impact event, blast event. Okay. So, good understanding of the constitutive material model is required, okay, so that the behavior of the material can be predicted under the dynamic loading. Okay. So, the effect of the SRS into failure and localization. So, increased SRS delays the onset of localized necking, this we have already seen. Okay. Since the stress increases, the local necking formation will be delayed, okay, and the void coagulance will also be mitigated, or it will be affecting later on. Okay. So, the total energy absorption capacity will increase, and it will increase the toughness of the system also. Okay. And several studies confirm that SRS influences the fracture strain and transition temperature in ductile materials under various loading conditions. Okay. So, the total strain at which the system is going to fracture is also affected by the higher strain rate effect, okay. And in turn the higher strain rate effect is also influenced by the temperature. At higher temperature, the SRS effect is enhanced. Okay. So, moving ahead. So, we are very familiar with the quasi-static loading. Okay. So, now we will see a comparison between the quasi-static loading and the dynamic loading. Okay. So, quasi-static loading. So, nothing is static. Okay. So, that therefore, we are terming this thing as a quasi-static loading. So, it is a very slow application of load, okay, typical in a standard laboratory testing. Okay. So, the inertia effect is not engaged. Okay. So, here we can see a quasi-static testing facility. Okay. So, here the specimen is located, okay. It is held fixed by a loading mechanism, and this is a typical compression setup. So, this one is applying a vertical load P on the system, okay, and the rate of loading is very slow. Okay. So, that is why we are calling this thing as a quasi-static loading setup. Okay. So, a dynamic loading setup. So, what happens in a dynamic loading setup? So, there is a rapid application of load, okay, typically in milliseconds. Okay. Milliseconds, why? Because our typical impact load, force versus time, or blast load. Okay. So, their application is in millisecond. Okay. So, since we have to mimic this type of effect of this loading into our material, our typical testing facility also has the application of loading in terms of milliseconds. Okay. So, the rapid application of loads such as impact, explosion or seismic events. Okay. So, it involves inertia effect, wave propagation and strain rate sensitivity. Okay. So, mass of the system, that is the inertia plays a vital role. There is propagation of the shock wave, okay, in the material, and the strain rate sensitivity, okay, that is the change in the inherent mechanical properties of the system with the rapid application of the load plays a crucial role. Okay. So, here we can see a dynamic testing setup, which is essentially a drop tower testing facility. Okay. So, we have a test setup. So, in the test setup, this is the specimen, okay, and here again is the fixture mechanism, and this thing, okay, this entire thing, okay, is released via a clip mechanism, and it falls instantly on this body, okay, thus mimicking a impact load. Okay. So, a comparison between the dynamic loading and static loading. So, in a dynamic loading it has higher strain rates. Okay. So, it increases the yield strength, energy absorption, okay, as we have seen earlier. In a quasi static loading there are lower strain rates. So, the yield strength remains to the static limit also. The good thing about the quasi static loading is that it is more predictable and it has a gradual deformation. The challenges in the dynamic testing, okay, in addition to development of the testing facility and the instrumentation facility, is the repeatability of the test, okay. And sometimes due to the intergranular defects, okay, grain size and all, the repeatability of the deformation is also not ensured, okay. And since this deformation are gradual and the mode of failure is predefined, okay. So, they exhibit repeatability. Here the repeatability is in question, okay. So, why it matters? Okay. So, material behavior like ductility, toughness, failure modes, they vary drastically between the two phenomena. Okay. In a dynamic testing facility or during a dynamic event, the material behaves with low ductility and the toughness is also low. Okay. Failure modes, though they are predictable during a quasi static loading, during a dynamic loading it can be unpredictable also. So, there is a vast difference between the behavior of the material under these two conditions. Hence, their understanding and their testing is very important. And when we have to design using such materials for any event like energy absorption, sacrificial devices or anything, we need to properly understand the behavior of the material under these dynamic conditions. Okay. So, a rate dependent determination is required. Okay. So, that is why this type of testing facilities are required. Okay. So, there is a very simple demonstration, okay, with a spring. Okay. So, we have a unstretched spring. Okay. So, during a quasi static loading, the deformation is uniform, whereas in the dynamic sense the deformation takes place at an instant on a very small area also. The other area has not seen this dynamic deformation, okay, and subsequently this propagation will occur. Okay. So, this compression phase again will propagate into the other phase. Okay. So, this is how the, in a very simple sense, the dynamic and the quasi static loading varies. Okay. So, experimental techniques for dynamic deformation, okay, depending upon the strain rate regime, okay, that is the application of the load regime. Okay. So, the different type of experiments have been devised. Okay. So, for very low strain rate testing, okay, like creep and stress relaxation, okay, tests like creep tester and conventional testing machines are available. For a quasi static testing, okay, hydraulic, servo hydraulic or screw driven testing machines are available. They are normally known as the universal testing machine UTM, which are readily available in all of the labs. Okay. Low dynamic events, okay, for low dynamic event, high velocity hydraulic or pneumatic machines are utilized. Okay. For high dynamic event, okay, split Hopkinson bar, okay, Taylor anvil tester or expanding rigs are used. Okay. For high velocity impact, okay, some sort of exploding foil is used. Okay. Realistic tests like explosives are used. Okay. Plate impactor are used. Okay. Pulse laser are used. Okay. Or inclined plate testing apparatus are used. Okay. So, depending upon which strain rate regime we are looking into, okay, this varies from the conventional testing machines to UTMs, okay, to high velocity actuators, to split Hopkinson particle tester, SPH bars, or to actual explosive testings. Okay. So, depending upon whichever regime we want to design our material or that material will be used, we have to test it in that particular testing methodology. Okay. So, the stress wave propagation. Okay. So, how the stress wave behaves and how does it propagates under the dynamic loading. Okay. So, under dynamic or impact or explosive loading, stress does not distribute instantly. Okay. As we have seen in the last graph, the distribution of the stress does not occur instantly among the entire system. Okay. What it does is that it travels as a wave through the material. Okay. So, if this material is there, okay, it will be traveling inside that material. Okay. So, if we are considering the different types of waves, okay, so there is something called a longitudinal wave, where the particle motion is in compression, elongation, compression, elongation. Okay. So, these are called the longitudinal waves. Okay. If the particle motion is perpendicular to the motion of the waves, okay, this is called a transverse wave. Okay. And there are certain surface waves which occurs, okay, in the topmost layer of the material also. Okay. So, these three types of waves are present, okay, compression tension, particle motion perpendicular to the wave motion, and particular motion occurring at the in a circular fashion on the surface of the wave. Okay. So, there are different wave speed equations, okay, that is how the wave is transmitting through the material. Okay. So, this is the typical one dimensional stress wave equation. Okay. So, E is the Young's modulus and rho is the density of the material. Okay. So, stiffer the material, more is the wave velocity, denser the material, less is the wave velocity. Okay. So, this is the speed of a longitudinal wave. So, this will mimic this wave speed in an elastic solid. Okay. So, as you have seen, there are longitudinal waves, shear or transverse waves. So, longitudinal waves are also compressive tensile waves, shear waves are the transverse wave that is acting perpendicularly, and there are surface waves or the Rayleigh waves. Okay. So, the use of these waves is crucial in the high speed impact. Okay. And using this measurement of this waves, okay, the material characterization can be done, okay, using different apparatus such as split Hopkinson bars and other type of apparatus. Okay. So, continuing with the stress wave propagation. So, stress wave propagation refers to the movement of a mechanical disturbance through a material after a sudden load such as impact or blast occurs. Okay. So, what does it mean? Okay. So, there is an unstretched spring. Okay. So, once this impact or blast hits this system, okay, there is a transmission of the waves, okay, in the form of longitudinal wave, transverse wave, surface waves. Okay. So, the stress wave propagation is the study of this waves. Okay. So, stress waves. So, there are elastic waves, there are plastic waves, and there are shock waves. Okay. So, elastic waves. So, the elastic waves occur when the material remains within the elastic limit. Okay. The entire system has to remain within the elastic limit. Okay. So, this wave does not cause any permanent deformation, as the name suggests, it is an elastic wave. So, there will not be any permanent deformation and they travel quickly throughout the medium. Okay. Plastic wave, the plastic wave formation occurs when the stress exceeds the yield strength. Okay. So, due to this shock wave, okay, if the induced stress is more than the yield strength, the plastic wave will occur. Okay. So, these waves move slower and are associated with the permanent deformation, essentially for the energy absorption in ductile materials. Okay. So, as the name suggests, as they are plastic wave, they will be associated with the permanent deformation. And then there are shock waves. So, these are the high intensity waves formed under extremely rapid loading. Okay. So, during an explosion, during an impact, this type of high intensity waves are formed. Okay. So, they are often accompanied by a nearly instantaneous rise in pressure and temperature. Okay. So, at the juncture, okay, where the load is applied, there will be an instantaneous rise in pressure and temperature. Okay. So, these are common in blast and impact event. Okay. So, the velocity of the elastic wave, velocity of the plastic wave and velocity of the shock wave, okay, they are roughly related using this relationship. Okay. So, propagating medium. So, all wave types need a solid medium. Okay. So, in order to travel, they need a solid medium. Okay. Shock waves can also propagate through gases and liquids. Okay. As in the case of blast, we have seen the shock wave propagates through the air or any other associated liquid media if it is occurring in the water. Okay. So, we will stop the topic here and continue in the next time. Thank you.